sorry, this is Z, and this is X. Okay. So if you look at MZ is going to induce a compression. We have analyzed it, so this is going to be minus. Okay. So from here, let's get the information that we need. Okay. And I'm also going to teach you how to use the help formula sheet. Okay. Yeah, posted. There's an important thing that you need to know. So we know that area is equal to pi r squared. Okay, so the area is pi. The radius is 30. So this will be equal to shift pi, hold on, 0.03 squared. So it's equal to 2.827 times 10 to the power minus 3 meters squared. Okay. And we know that Ixx is equal to Izz for the circle. So if I were to pull out the formula sheet, okay, so this is from the formula sheet that you will be getting, that you have seen before. Okay. So this will be equal to pi over 4 multiplied by radius to the power 4. Okay. So this is pi over 4, 0.03 power 4. Okay. So 0.03 power 4 times by shift pi divided by 4 is equal to 636.173 times 10 to the power minus 9 meter 4. Okay. And then I'm going to write down a relationship. Because we have a torque, we need to find the second polar moment of area. So J is equal to twice of I. Okay. So that's why I only gave the formula for I. I did not I did not give for J. So just remember J is equal to twice of I. So this is 2 multiplied by 636.173. Now this is for shaft, yeah. I mean, polar moment is also always for cylindrical stuff, right? So this will be equal to 1.272 times 10 to the power minus 6 meter 4. Okay. So I have everything already. Okay. So now we are going to find what is our stress Y at element H, right? So minus Py, our Py is equal to minus 12,000. Divided by cross-sectional area, which is equal to 2.827. Now this is the easy part, okay? The breaking down of the what is a moment, what is a axial force, what is a shearing force, that is the difficult one, okay? So now there is a moment about Z, I forgot the number. Sorry, moment about Z is equal to 1800 divide. The good thing about shaft, Ixx, Izz is the same thing, okay? So 636.173. And then multiply by the radius. So this is equal to 12 power 3 divided by 2.827 power minus 3. 4.245 minus times 10 to the power 6 minus by 1800 times by 0.03 divided by 636.173 power minus 9. 84.883. So this will be equal to 84.883 plus 4.245 is equal to 89 minus 89.128 times 10 to the power 6 Pascal. Okay, so let me do everything again. 2.827 power minus 3 plus 180.903 divided by 636.173 power minus 9. Yep, 89.128 is good. Okay, so we have found our axial load or our normal stress. Next, we are going to find the shearing stress. Okay, so if we were to, if I were, now this is a lot of, I mean, we have done thin wall before. This is not thin wall, this is thick wall. How does it work? Okay, so now we are going to view from XZ plane. Okay, and I'm going to draw the shaft of interest. Okay, so this part is where over here, this is our centroid. Okay, and we know that the 5 kilonewton in the Z direction is going to, where do you get 0? Oh, the shaft diameter is 0.03, shaft radius is 0.03 radius. Okay, that's the radius, Arisha. The question asked is where do we get? So this is the radius. Okay. So we have a force coming down this way at 5 times 10 to the power 5 or 3 Newton. Okay. And we have our element H over here. Right. So there is also shear flow going down. Okay. So the shear flow, the Q will go down this way. I mean the whole area. Okay. So the whole area will see shear flow going down this way. Okay, so the shear flow is going from left to right. Okay, so we are going to calculate what is our shear flow. Okay, so we are going to calculate our shear stress. The plane intersecting axis is Y, right? And the direction of the shear stress is going down in Z. Okay, so we are going to look at element H. Okay. So this is equal to, again, the formula is VZ over IXX QX divided by thickness. Okay. So now we know what is our Vx. Okay, Qx we don't know. Qx is equal to A Y bar or A Z bar. Sorry for this case. Okay. So the area that we're going to consider, I'm going to use in red. Okay, is this area now? Because H is over here. This is the area. It's a semicircle area. We're going to find out. So we know how to determine area, right? Then we have to find some point over here. There is our centroid of the semicircle. This is our Z bar. Okay. Right. So the area is the easy part. So area is equal to half pi r squared. So this is half. We did pi r squared before. This is 2.827 times 10 to the power minus 3. Right. So 0.5 times 2.827 power minus 3 is equal to 1.4135 or 1.414 times by 10 power 3 meters squared. Okay. So the Z bar will be, so you go to the formula sheet. I'm going to bring the formula sheet. Come on, UG. I'm going to bring the formula sheet down. All right. So you can see that the formula sheet says that this is 4r over 3 pi. So we know that z is equal to 4r over 3 pi, right? So I'm just calculating the value. In fact, there's an easy way of doing this. I just realized that. So 4 multiplied by radius divided by 3 pi. Okay. So 4 times by 0.03 divided by 3 divided by shear pi is equal to 12.733 times by 10 to the power minus 3 meters. So Qx is equal to a z bar. So this is equal to 1.414 times 10 to the power minus 3 multiplied by 12.733 times by 10 to the power minus 3. Okay, so 1.414 power minus 3 times by 12.733 power minus 3 is equal to 18 times 10 to the power minus 6 meter cube. Okay. As I said, I was trying to too much of a rush. If you look at the formula, Qx, so area is pi r squared over 2, right? And the y bar is what? 4r over 3 pi. So if you can cancel this, cancel this, cancel this, cancel this, the formula finally is 2r cubed over 3. Okay. So you just put 2 over 3 multiplied by 0.03 cube. Okay. It's going to be the same value. 3 times by 2 over 3. It's equal to 118 times 10 to the power minus 6 meter cube. Same thing. So from here, we can calculate our shear YZ at point H. Okay. Now this is due to the shear force. Okay. So you have V is 5 times 10 to the power 3. Then you have our Qx. Qx is 18 times 10 to the power minus 6 divided by your I. What is our I? Hold on, I need to find our I. Our I, maybe it's over the other side. Our I is 636.173. 636. And then the thickness will be the diameter. Okay, so this is the thickness now. Okay, so it's equal to twice 0.03. Because 0.03 is the radius. So 5 power 3 times by 18 power minus 6 divided by 636.173 power minus 9 divided by 2 divided by 0.03 is equal to 2.358 times 10 to the power 6 Pascal, and the shear stress is going towards the right. We are going to follow the shear flow, okay? It's going towards the right. So 5 power 3, let me do it again. Yep, 2.358, okay? Then the next one, so the first one we are calculating, this is due to Vz, okay? So that's another one, okay? Next one is due to the torque. Okay? So I'm going to use the same circle due to the torque now. So we know that, again, this is our centroid, okay? And we are aware that we have a torque going in this direction. Okay, wait. Doing in this direction. And this will be our Ty, right? And here is our element H, right? So the shear, again, YZ at point H is equal to Ty multiplied by the radius divided by J, right? So Ty we found, and I could not remember what's our Ty. So Ty is 750, right? 750. Our J is twice of I. Okay, so twice of I think we calculated that, which is equal to 1.272. And then our radius is 0.03.